Hello and welcome to MECS Research Today, the show that's dedicated to discussing new developments and research in the fields of education, music, science, and technology. I'm your host, Daniel Szeligowski, and today we're going to talk about my current and upcoming research just as an introduction. I'll be discussing general adversarial networks, multidimensional data visualization, and visual audio manipulation. So to kick things off, let's have a message from our sponsors. I'd prefer to keep it at the beginning of the episode just to keep things moving and so that there's nothing in between the discussions. Just as a brief introduction to myself, I am currently a Bachelor of Music in Choral Music Education, as well as a Master of Science in Computer Science. So one of my current big topics of research is generative adversarial networks, also known as GANs, and their utilization for creating music artificially. So a big research paper that I had done last year was on the idea of turning neural networks into renowned composers. So there's current research such as OpenAI, Jukebox, Google Doodle did a thing themselves using this same sort of idea, using a GAN network to create music, either given a simple melody line or pre-existing audio, such as with OpenAI Jukebox, where the first certain number of seconds of a song are played, and then the artificial intelligence will try to fill in the gap between that section and the next section of the music. What I focused on researching was creating actual original compositions based on the compositional style of classical composers. So the focus of my own paper was on Niccolo Paganini and his Capriccios for violin, which are a set of virtuosic violin pieces that are basically just meant to demonstrate, extreme virtuosic technique. And for creating something like that, just using an artificial intelligence, I knew would be a challenge and also a good demonstration of what is and isn't working at the current point in time. So a big part of my research was looking into why are we having such a difficult time with creating original sounding music using these neural networks. And one of the big things that I found was, especially for like Google Doodle's example, was they trained a neural network on like 360 some of Bach chorales. So they trained this artificial intelligence on 300 some MIDI files of Bach chorales, which is just a 4-voice choral piece. And they made a simple Google Doodle where you would write a melody line and it would write the other 3 voices for you. Now, the big issue with this that I was able to find in my own research was training on such a large data set is very problem-filled. I found that going from the full set of 24 Capriccios or Caprices to smaller, more fine-tuned sets was a lot more effective in creating original compositions. So the big issue that I found was anytime that I had trained my artificial intelligence on a sequence, let's say 32 notes out of maybe 100 in an entire caprice, if I wanted it to listen to all 24 caprices and attempt to, analyze 32 measures at a time or 32 notes at a time, whatever the case may be, the artificial intelligence, when it was tasked with writing its own composition, would eventually start to fail after those first 32 notes or 32 measures or whatever it may be. And the way that I ended up solving this was I had attempted modifying the number of notes that it studied beyond 100, so it would study pretty much the entire piece based on the shortest duration of all of the pieces together. So I think the shortest out of all of them was 140 notes compared to like 200 some was the average. So training it to create compositions and analyze compositions based on that 100 some limit was more ineffective than just using 32. Anything less than 32 was problematic because at that point, anything less than 32 notes didn't have much of a similarity in any sort of patternistic compositional technique that the artificial intelligence was able to read and sort of gauge what to do next at any given point, which is sort of the big problem with generative adversarial networks just in general. We can train them to have what's called a LSTM, or long short-term memory network, but the issue is that given the size of that short-term memory, once they get beyond that little bit of memory, then they run out of ideas on what to do. Or if they're trying to go beyond their capabilities, then it becomes problematic. So by reducing the number of notes that it was tasked to compose, it usually had a much better flow. Anything more than 32, it would usually just end up repeating one note over and over again. And that may just be a problem with the compositions that I selected because there's a lot of repeating notes. But I think that's going to happen regardless, just because it doesn't know where else to go. The other issue was that in creating these compositions, trying to get it to create longer compositions, even with a shorter series of notes, was also problematic. So the issue that I found was anytime that I trained this neural network on the entire data set of 24 pieces, they were so dissimilar that even creating a long piece just was troublesome, just in the fact that all of these melody lines that it had studied, many of them were completely unrelated, and especially in different tonalities or different keys, or had different tempo, pacing, all those different sorts of things, different rhythms, all of which did not line up well in the long run for longer compositions. What I ended up having to do was break down the compositions into smaller sets based on their musical similarities. So I created different sets that were very slow, of similar key, and ones that were very fast and of similar key, as well as a similar rhythm. This made all of the difference. Breaking these compositions down by their musical similarities yielded much better results. The issue with that is because there were so little examples for it to go off of, it would usually take some aspects of each composition and sort of blend them into one, which doesn't necessarily give an original composition based on the melody line so much as it does embellishing it, which was not so much the issue with the larger data set. With the smaller data set, I was risking entirely recreating one of the compositions or having it recreated but slightly embellished, which sadly with the current point in time there wasn't much of a way around that. And that's one of the big issues going forward is we need conciseness in data sets, but there also needs to be enough items in the data set to allow for variety so that we can actually train music based on compositions that are similar but also have similar rhythms and are also different melodically. In doing this, we can actually break things down, train it on a shorter series of notes, let it create a melody line based on a shorter span, maybe a 3-note motive or a 4-note motive. And even still, the issue with this is that we don't have much control over what the neural network is actually going to produce. I don't have any way to control, at least indirectly, the key signature. I can't really control the tempo, the key that it chooses. I do have the ability to say, okay, here's the first 8 notes of your melody line, generate everything from here onward. But that sort of takes away from the uniqueness if I'm trying to write a melody line for it. And that was one of the big things that I wanted to solve. The phone company Huawei actually did, as a demonstration of one of their newer phones, they had trained a neural network on Franz Schubert's Unfinished Symphony, which just has the first two movements and no third or fourth. So by training a neural network on those first two movements and having it write a third and fourth movement based on what it already heard, it was able to generate something sort of musically similar. But a lot of it, they actually had an orchestra professionally record this full composition now that all four movements were available. But the orchestra director also had to make changes for it to be musical, which, again, is trivial, and that's what we're trying to avoid. The goal of my research was to remove the need of a third party in producing these compositions. And something like that could potentially work out if we had a composer that had, let's say, 9 symphonies, like Beethoven, for example. If I trained a neural network on the third movement of all of Beethoven's 9 symphonies, and I said, okay, write the third movement of a 10th symphony or theoretical 10th symphony, or train it all on the first movements of all 9 symphonies and have it write the first movement. Training that as 4 different data sets would be much more effective, as well as the fact that, classical music is very formal. Each section of a symphony, at least in the Romantic era symphony, has its own division of what sort of style is it going to be for each movement. Is it going to be a sonata? Is it going to be a minuet or a scherzo or a choral piece that also has, a symphonic work like Beethoven's Ninth Symphony? Things like that are things that are much more difficult to get a hold of, especially, again, working with such a small data set. Uniqueness is an issue. Musical similarities, they're all in different keys. They're probably all in different, tempi. The rhythms are going to be very, very different between them, albeit they're melodically similar only because of their musical form. And that's sort of where we need to go from there. So my future research that I plan on doing with this is going out and finding, let's say, 60 art songs, taking those and grouping them by maybe their key, their tempo, rhythmic patterns, and creating a more concise group of compositions. Something like waltzes, for example, would be a good fit because they're all usually within, triple meter or 3/4 time generally. So the accents are going to be similar. Melodically, they're going to be pretty similar. Harmonically, if it's all the same composer, they may be fairly similar. And I think narrowing it down to be more concise is probably the way to go. Beyond that scope, beyond waltzes at least, my goal is to eventually do some research regarding actual German art song generation. So I'm going to train, for example, a generative adversarial network on all of the piano parts and vocal parts of, let's say, Brahms's 70, 80-ish art songs. And beyond that, having it have a secondary adversarial network that focuses on generative text. So having a generative network that is fully trained just on German art song poetry and having it pick up on German syntax, try to create its own German art song poetry that is combined thereafter with the generated music. Obviously, there's 2 big issues with this. How am I going to line up the text that it generates with the melody line for the vocalist by the other generative network? That's going to be a bit of an issue, as well as even if I tried to sync them together, Programmatically, I'm not sure how I would do something like that. Um, Having them do both of those things at the same time and trying to sync them together, it's not really feasible to some degree because it's such an opinionated thing as to what word should be held for such a duration, um, and trying to come up with a way to emphasize certain words of text. Um, if I'm working with a poem, I want to make sure that I'm emphasizing a word that matters and not just some random word. That sort of preciseness is the biggest difficulty, I believe, in generative music, and that goes for OpenAI Jukebox's research as well. Is they can take a melody snippet or an entire song just based on an MP3 file and have it generate another 30 seconds or so of music, but the singer is going to just sound like garbled audio, just because of the voice being another frequency, but there's no language aspect. And having it tie in that language aspect into a melody line is a bit difficult. But nonetheless, that is where future research should lead. Um, Anything beyond that, getting into the nitty gritty of, well, how do we get rid of the need for conciseness in training these musical data sets? Maybe starting out with something that is just one single voice, such as like um, Gregorian chant, for example, or um, anything along those lines, like what I had done using the Paganini Caprices. Anything where there's multiple, at least hundreds of examples that can be filtered out based on their musical similarities, breaking them down and organizing them and training um, generative adversarial networks on each individual broken down data set. So one data set for all of the slow pieces that are in C major, one for all of the fast pieces that are in D minor or something along those lines. Breaking down data sets from larger sample sizes will at least give us something more dense to train these networks on. And that's, I think, where we're headed in that direction. Beyond that, it's going to be a little bit more difficult to create something entirely unique based off of training smaller note samples versus larger note samples. Again, that little bit of fine tuning or that alpha feature um, is going to be troublesome, sort of no matter what. And I think as far as we get in research, that's going to be an issue for the next probably at least 10 or more years until we can find a way to fine tune these things without the need for, conciseness and just breaking down a way to train an adversarial network based on musical examples. Say, have it pick a key, have it pick a tempo, or have it pick different meters for different sections of the music, have it plan out like an actual composer would, how it's going to fill in the blanks of a composition rather than how can it continue off of the next pre-existing pattern in its memory. So my other big topic of research that I focused on last year was on multidimensional data visualization. For most people that are familiar with data warehousing, this would be referred to as an OLAP cube. OLAP is a system used for modeling multidimensional data, usually in a sort of cube form that breaks down data into 3 dimensions rather than 100 or more sometimes, and reduce it into a more searchable aggregated data set. So the point of my research was focusing on open source applications for visualizing and aggregating these data sets. There's not many non-commercial open source data sets that are data visualization tools, I should say, that exist for such a thing, and the ones that are out there are fairly flawed or are very tedious or have very unique requirements. Some of the main ones that I had found, there are some Python libraries, as well as a program called CubesViewer. Big issue with those, as well as other web-based applications, which was sort of the main principle I had in mind, was something that was cross-platform because it was web-based. The big thing that I found was that a lot of these applications had a sort of double back-end system. One of them, for example, the Python-based one, utilized a Python library to do all of the data manipulation and have it serve back to a web page or application or whatever it may be implemented on. But that Python library had a built-in Java backend, which seemed counterintuitive to me, especially working with large data sets. The big issue that I found was this double backend thing just kept reoccurring, and with that, you're risking oversimplified data, as well as the time necessary to compute these things. Anything using two back-end systems is going to be much, much slower than one single application. Python alone is already a slow language, and Java isn't too much better, but it's not too bad. But having an interop between the two of them is a bit counterintuitive, I believe. The other one, CubesViewer, used JavaScript to perform most of the application's actual operations, except for actually serving the data cube or the data set, which is essentially just an Excel table that has multiple columns. Used a backend server system called CubeServer, which sadly once again was written using Python, actual arithmetic operations, and doing all of the data aggregation. All was done through Python. So rather than having a Python to Java interop, we now have a JavaScript to Python interop, which, again, is difficult. Working with a language like Python to Java, well, Python is single-threaded, but Java is multi-threaded. Okay, that's not too bad. JavaScript, which is single-threaded and does not have support for high-precision data, Python, which does not have native support for high-precision data, both are single-threaded languages. Not only are you losing data precision, but you're also losing the efficiency of concurrency. And that was the big topic of sort of my halfway point research paper, was the difference that it makes in visualizing and computing massive data aggregations compared to something single-threaded versus concurrent. The hope that I had was to create this application myself using WebAssembly, ideally. My idea was to write something in like a C# or Golang and have it compiled directly to WebAssembly. Have an HTML5 application that would perform the actual visualization, plotting things on a canvas and using some CSS manipulations or SVG, for example, but using JavaScript just to call these WebAssembly functions that would perform the actual data aggregation. I would be saving on losing data inefficiency, as well as the ability to have concurrency in the web browser, because WebAssembly supports it. I believe it's through shared memory concurrency. So it is possible to some degree, at least in theory. And that's what my test found. It was much more efficient to use something like WebAssembly over JavaScript and WebAssembly over Python. I think in some test cases I found that WebAssembly was actually faster, or almost as fast as C in the browser, and ran almost at near native speeds compared to C on an actual desktop client. So the performance is there with WebAssembly, but the functionality is not quite ready. And to say the least, I found that same issue to be true in programming my actual visualizer. So I wrote a very simple Python script. I think it fit within like 200 lines of just performing these data aggregations. So either aggregate down by a certain data piece or dimension, drilling down to scope inward on a certain dimension, rolling up back outward into a different dimension, as well as finding the summation of some aggregate or the number of rows that a certain dimension has relation to, any number of things. All of these manipulation tools all were sort of the main point of the OLAP system and OLAP cubes in general, was to be able to very, very efficiently aggregate data and visualize it, see it as an Excel table, see it as a graph. So I used Matplotlib to just draw out basic graphs. I wrote the same thing in C# just to demonstrate the difference in speed versus single-threaded to concurrency, which obviously C# alone was faster than Python, but C# using concurrency was even faster than that. The issue that I ran into, well, aside from the fact that there's not many very good graphing libraries for C#, I ended up using Oxyplot, which was the closest to Matplotlib. I was able to write a fully functioning demo. It was much more code. However, compiling it into WebAssembly was very difficult, and in some cases actually ended up slowing down the process, as well as issues of using C# with WebAssembly in the browser. I was able to call C# code compiled into WebAssembly, but in order to do so, I had to use Microsoft's Blazor framework, which, again, is a newer framework, and there's a lot of things that are missing in it. So I tried writing the same program back using just the Python script, so no double backend, but it's still in Python. I tried using a Flask application to do so. I had a web page that would be hosted using a Ruby server just because I wanted something different so I could see in between the two. And the web page would take in these server requests and post them to the same page. So if I'm on one single page of a website and I push the aggregate button, I don't want it to go to another web page that is now aggregated. I want it to perform that operation on the exact same page. Well, that's possible, but actually performing these calculations using HTTP requests and trying to pull all that data backwards, a lot of it was just getting lost in translation and just does not correlate well. Getting the HTTP requests to come into Python wasn't difficult, but getting them to come back outward, back into JavaScript, and having to go from, I suppose, Python to JavaScript to actually manipulate the data that Python returned, well, I have to decide what sort of memory storage I'm going to store it in, whether it be cookies or session storage or local storage or something else. And it just didn't end up working. So the next probable thought that I had was to use a language like Golang. Golang has concurrency. It's got great built-in support for web development. It's got great support for like web server hosting, as well as HTTP framework stuff is all built in, except for the fact that it does not have generic typing. And also there's a lacking support for more complex math libraries, something like NumPy and Python. Lacking math libraries and lacking graphing libraries. Graphing wasn't my biggest concern, but actually performing the operations was nearly impossible, because if I import my Excel table, well, I'm going to have these matrices essentially of multiple dimensions that have strings, integers, doubles, floats, single chars, or characters, they're all going to be mixed into one big data table, and I can't do that in Golang. Um, there are some ways to get around it using the interface type that exists in Golang, but that only goes so far. It's just barely enough practical to be able to create data structures like a linked list without using like pointer typing. Um, so we have pseudo generics, but generic typing is still being implemented in Golang. So although I was able to create this Python script that performed these operations, and a C# one that did the same thing as well, I was never able to get anything actually working in the web browser. So it was all just a local script. Obviously, something like that with C#, for example, I can embed into an actual desktop application and have it just be ran that way, but then I'm losing a lot of cross-platform support. I would have to make individual containers for a Windows environment, a Mac environment, a Linux environment, Android, iOS, and that's what I want to avoid. I want to be able to visualize data across platforms, write once, run anywhere sort of idea, and sadly that sort of thing isn't quite feasible with where programming languages are currently at, which was a unique issue that I didn't expect to find. So just to recap on that, the two main problems were that these languages were lacking in necessary programming features like generic typing and multi-threading support, as well as the fact that Python is one of the few languages that actually has a very, very well-developed math library and graphing library, especially for cross-platform usage. My hope was that Golang would work out really well because I could make a single Golang application that would host and serve the web page and perform all of the aggregations. But also the fact that I could compile Golang to WebAssembly, which from my first research paper ran faster and was much more efficient, especially using Golang with concurrency in WebAssembly was even faster, and I believe outperformed C# potentially, at least on the desktop side of things. So I was really hoping that that would work, especially because Golang has very, very good support for concurrency using their channels, except for the fact that there's no generic types. Class typing is also a bit of a difficult challenge since Golang is solely struct-based. Since it's primarily a functional style programming language, it's more so like C, where it doesn't have classes. There's pseudo classes using structs, but again, a lot of those features are lacking. And that's not necessarily a problem with the project that I was working on, but having those features missing in something like that in such a high-level program is a bit difficult. So where we can go from there, I suppose we really just have to wait for the languages to develop. So my hope is that within the next year or so, I believe generic typing is in the works by the Golang team at Google. Hopefully we'll see something on that soon, and when that day comes, maybe I'll be able to rewrite that program and actually have it as an independent web application. So my last big topic, which is fairly open-ended, is visual audio manipulation by conducting an artificial intelligence ensemble. So what I mean by that is I want to be able to, at least from a musical conductor standpoint, if I have, let's say, a MIDI file, or if I'm using a VST that has more realistic sound, something like Spitfire or Eric Whitacre's VST for his choir voicing, or anything that has artificial voice generation for actual language. Those sorts of things I want to be able to manipulate as a conductor rather than just hand manipulating different points in time in the sound. If I want to write an orchestral piece and I want to hear how it's actually going to sound when it's played in real life, there's always going to be a difference in something that's recorded by a live orchestra versus something that's being played back by a VST orchestra. And that's sort of the gap that I'm hoping to bridge. Um, there was some research done in 1998 at MIT in analyzing conducting gestures. So, using your right hand to control the tempo, the flow of time, the beat of the music, the pulse, the dynamics, all of those sorts of things, using hand gestures. Those sorts of things, however, are also fairly both objective and subjective. There are rights and wrongs in conducting, but there's also things that are very opinion based, and that's where it becomes difficult. So, in recording these gestures, they were able to train a neural network on recognizing the patterns between conducting one versus conducting two, for example. And something like that is not necessarily too difficult. Conducting patterns are meant to be very clear as to what number of beats that you're in. If I'm conducting in 4/4, I'm going to conduct a 4-beat pattern, for example. The issue with this is that there is a blurred line for the type of expression that I'm conducting. If I'm conducting very connected and smooth, which is known as legato, versus very sort of plunky and percussive, which is known as staccato, something very disconnected and sharp, not quite as smooth, that's also a bit more challenging. Something that's very smooth and connected may look, if it's 4 beats, it may also look like it's 3, just because of the way that the beats are blended together. And also, it's clear for us as people to see where the beats divide. But for artificial intelligence, it's not going to be quite as clear when something is expected to happen. If I'm conducting 1, 2, 3, 4, I want something to happen on 1, 2, 3, 4 very clearly for my ensemble. If I'm training a neural network to respond the same exact way, if I have a very curvy conducting pattern that I'm conducting, well, where beat 1, 2, 3, and 4 are is not going to be quite as sufficiently clear as I would expect it to be. And it's going to differ by conductor. It's going to differ by the composition. Everything is going to differ, especially by the experience of the conductor, as well as the artistic expression that the conductor is trying to employ. Some further research was done in analyzing these conducting patterns based on their shape and sort of musical texture. A study was done based on novice conductors versus professional conductors. And even still, if they were conducting the exact same pattern, there was a clear difference in the way that they were shaped and the way that they looked, even as to where the beats were, was a bit more unclear. So training a neural network on something like that would take a lot of sample data. As well, we would have to train a neural network to respond to different styles, not just on different beat patterns, but different conducting styles. And that's just in the right hand. So my hope is that I can train a neural network with computer vision to actively respond to different beat patterns based on the number of beats, but also see the relation between how connected a beat is versus how percussive or accented it should sound. And obviously, that's something I could do if I'm writing sheet music. That's something I can easily do. But if I'm playing back a VST in something like Fruity Loops or GarageBand or Logic Pro potentially, I don't have quite as much liberty to just go in sort of note by note as I would in a sheet music editor like MuseScore or Sibelius or Finale, and actually place accent marks or draw slurs to connect different notes in the music. Those are all very difficult things for a musician. There's all different difficult things for conductors and composers, and especially for machines, obviously. So finding a way to bring those together in a cohesive manner that is also very clear as to what the conductor wants. Obviously, early on in a research project for something like this, there would have to be a lot of afterward correction, just like the generative adversarial network with Huawei and their orchestra example, where they had an actual orchestra director go through and make modifications to the score that the AI generated to make it sound a bit more musical. Those sorts of things are going to be necessary, I think, at first for something like this. And other things have been done similarly. There are connecting music museums out there. I can't remember which one it is, but there's one that features a playback system where a conductor can sort of conduct just to get the pacing going for something that's being played back. And that is a start to say. But again, that sort of thing is going to be very difficult. If I'm training a neural network to look and recognize these different conducting patterns, well, I can train it to figure out how many beats I'm conducting. Not too difficult. Training it to understand the expression that I'm trying to give, whether it's connected or disconnected, or very pressed, or very timid, or intense. All of those different things are troublesome, but not impossible. Having it keep track of what would be called a retardando, or rubato, or accelerando, so either slowing down the music or accelerating it at will. If I'm recording a conducting pattern graphically, I don't really have a very sufficient way to record that visually, unless also at the same time I'm recording the velocity and acceleration of my hand gestures. So these are all very difficult things, and that's just for the right hand. The left hand as well could be any number of different things. A lot of the times conductors will use their left hand to perform cutoffs. They'll use their left hand to raise the sound upward to increase the volume, or lower it downward to decrease the volume. They might make a sudden stop with their palm. All sorts of different things. And again, those are something that's going to differ conductor to conductor. So in something like this, if we wanted an actual practical application for virtual musical ensembles that are produced by VSTs and DAW software, all those different things would have to be trained ahead of time before actually being able to produce a valid sound, to say the least. Now, something like this, there is probable cause to expect that something like this would have to be commercial, essentially. A lot of these high-level VST programs are paid for. They cost quite a bit of money, along with the notational software, the playback software, which is all going to be difficult to create in one big open source application. And creating a neural network that responds to these modifications and being able to use it across the board would almost have to be a piece of software on its own, which is probably where the greater difficulty is. I can't just plug in this neural network into any old piece of playback software, or even just a plain DAW or DAW. I would pretty much have to write it as a plugin on an application-by-application basis, which would be extremely tedious. Either that, or someone makes an application that is specifically for that one example. These sorts of things aren't very popular in the research world right now, but I think it'll eventually start to pick up, especially with the rise of virtual ensembles. Um, because of COVID, I believe that people are probably going to get a little bit more into the technical side of artificial intelligence and its use with music, especially if I could have something to not just do musical editing, but also video as well. If I have 60 people all send in um, recordings of themselves singing, if they are all singing the exact same volume and they're just singing the words on pitch, for example, if I can train an artificial intelligence to perform the audio manipulations that I'm conducting, then I don't have to worry about different modifications being made by the actual performers themselves. Obviously, that's a bit of a cheat, but in short term, that's something I could potentially make very quickly compared to rehearsing an ensemble for months and months at a time. Or if I'm switching conductors on an emergency level sort of thing. Not only that, but also if I could find a way to have it edit the video to sort of match these different expressions. Um, that sort of thing is getting into a whirlwind of its own. But I think with deepfake technology, that's a potential as well. We could have deepfaked performers where it might be their same face, but different expressions are deepfaked on based on the character of the piece. All those sorts of things are very possible. It's entirely possible that someone could create an entire neural network produced opera, for example. If I were to train a generative adversarial network on enough operas to have it write its own script, have it write its own music, and then take some potentially 3D models or motion capture models of someone and deep fake different facial expressions on to match the theme of the music and the artistic expression of the music, and have an ensemble that also follows the conductor. I could be a conductor of a neural network ensemble that's performing an entire stage work at that point. And obviously something like that is far, far, far in the future. But I don't think by much. Um, I think with the direction that current research is going in generative adversarial networks and computer vision, I think we've got a lot more potential open cases for some pretty extravagant research projects. Something like that obviously is something not just one single person should be working on, nor is it just a single dissertation project. Something like that would take many years of research to develop, and that's where things sort of have to be taken one step at a time. But I think if we can start working more towards visual audio manipulation, not just by conducting, but by simple gestures of some sort, that sort of principle can be applied to other things. For example, visual picture manipulation. If I am using sort of like a hologram thing, if I have a screen that has an image and I want to manipulate that image based on some hand gestures rather than having to manually go in, mouse and keyboard and draw out something or lasso out some piece that I want to snip it out. If I want to just do hand gestures but train it on some hand gestures to mean different things, that's potentially practical for a real world application. And especially coming down to the side of people with disabilities, that sort of thing would be very practical for someone that wants to do those sorts of things but isn't able to. I think visual manipulation of technology, just in general, is something that we're going to start seeing a lot more of in the future. Hopefully so, but I suppose we'll find out when the research gets to that point. But obviously, the other big issue with something like that is the fact that something like musical conducting is a very psychologically subjective thing. Again, something like that would have to be trained on a conductor basis based on what their gestures mean or what their musical intents are, which again, it might be the same for one conductor, but their gestures and their different expressions may change based on the piece that they're conducting, or the era of the piece that they're conducting, or any number of things, for example. Not only that, but it's such a psychological subject just in general. It's hard to say how conducting affects people psychologically just in general. There's not too much research on how it actually affects an ensemble. We just know that it happens to work out. But that's another bit of research sort of pathway on its own, I suppose. So hopefully we'll see more research on the psychology of conducting and conducting as a means of visual audio manipulation, sort of augmented reality style thing, just in general. But for now, that is about the extent of my current interest in research. Obviously, there's other things that I'm working on, but those are sort of the primary things that I've been looking into over the last year. Beyond that, for the rest of this podcast, my hope is to bring some other people in, discuss some new developments in different technological fields or scientific fields or humanities fields, based on what different co-hosts might be interested in, as well as I plan on bringing in a few professors, interviewing them, finding out what their research interests are, what their current research is based on, things that they're currently looking into, all those sorts of things. So that's something to look forward to in the future. So just to recap, I've discussed my current research in using generative adversarial networks to compose classical music, covering issues with multidimensional data visualization, as well as visual audio manipulation using artificial intelligence. And if you're interested in new developments in music, education, technology, or science, or you just find the subjects interesting, feel free to follow MECS wherever you get your podcasts.